gather?
Because the Dunbar's number for the hunter-gathering groups, it's not evolved to the modern humans. The number is doesn't variable in for example in the Homo erectus, I think the Dunbar's number is around 146, and in the modern humans is around 100. In the Homo sapiens, the Dunbar's number is around 150. For example, in the great apes or chimpanzees, I don't know the exact, but the Dunbar's number is around 70 fifth nodes or individuals, and the chimpanzees has if I don't do a mistake, the chimpanzees has the very large communities in the most large community in the animal kingdom. That is the half of the Dunbar's number for the modern humans.
There's only one Dunbar's number, which is 150. The other is group size, in which there's bonding between the individuals, so they recognize each other as individuals. So it's not just flocking. I mean, it's more than that. And what he did was to correlate group size with a ratio of brain size, and then on that ratio, he looked at human brain size and then calculated what is the predicted group size if we just looked at this biological correlation, and that's what 150 is.
So what exactly in your model does it say that we're dealing with humans and not chimpanzees?
Como dijo el profesor, the Dunbar's number is for humans, and we take in the hypothesis that we want to check if the Dunbar's number is correct, because the Ritz model is doing for humans population. Antonini and Seth Bullock do the Ritz model for model human communities.
But it's more like, to some extent, we're fine-tuning the model such that there is this, you can say maybe phase transition or something like that, at the number of 150 individuals, given the parameters of the model and the energy constraints. So obviously if you change the energy value to higher or lower, you would change the point where the network doesn't converge anymore to complete cooperation. Right? So that's what he showed. When you lower the energy, actually less than 150 will converge even in the 150 case. But what's interesting here is that by having this model and by being able to play with the energy parameter in such a way that we can fine-tune the threshold between full cooperation and then in higher network sizes almost randomness, right? It was 50-50 whether the nodes were one color or the other. We're basically simulating the biological scenario until 150, and then after that basically we need other mechanisms than just local interactions between the nodes in order to guarantee high levels of cooperation. So the next step of this project will be to say, now that we've generated a test bed in which biologically 150 is an optimal number for human populations, what happens in communities that are bigger than that? Obviously, if you just have local optimization, then we won't get the global cooperation. But we know that at least by the time of the Neolithic period, people were in bigger groups than 150. So at some point, Dunbar's number doesn't apply anymore. Humans were somehow able to exceed this number, even though biologically it seems to be like a limitation. And then people have theories about how this is possible. It could be religion, it could be warfare, it could be the agricultural revolution of forcing people to be sedentary and living together in communities and these kinds of things. And so basically the idea is that let's try out some of these mechanisms in these larger populations where we have a breakdown of cooperation. In particular, it would be something close to what Susanna discussed in her paper about the research mechanism, because obviously the Hopfield network that she talked about it's the same Hopkins network that we're running on topologies. Just in one case we're talking about neurons interacting, in the other case we're talking about social agents interacting. And so, to some extent, the hypothesis is that the origin of ritual behavior and group ritual is related to the threshold of exceeding 150 people in the social groups and requiring other mechanisms to ensure cooperation other than just, let's say, a biological predisposition of cooperating in that kind of group size.
There's even, I think, a hypothesis about language, because I don't know if it was numbered, but someone correlated it with the thickness of the prefrontal cortex.
That's right. He looks at the ratio between the prefrontal cortex and the rest of the brain volume, something like that. That's the we look at this.
Like I do not remember the name of the neuroscientist, but it was a researcher that said that the way to couple with more people than the numbers number was to invent language, like a communication pattern that changed the structure of animal communication as it was seen, for example.
Okay, yeah, so language could be another option.
And I think it correlates with the time in which we started evidence for linguistic achievements or communication in humans.
Yes. We have a challenge to try to model that in this kind of simplified system, like the origin of language. But if you do something like the Watson reset model, and suddenly we find that even in 500 nodes, given the energy limitation, the social reach limitation, and so on, suddenly we do find conversions again to global optimal patterns. That would then put a very kind of alternative interpretation of religious behavior, because at the moment the cognitive science of religion thinks of rituals and all these kind of things as maladaptive side products of theory of mind modules. That we think that basically it's just over socializing the world because we need it to be social in order to exist in groups, something like that. But that really there's no adaptive value for engaging in group rituals as such. But what we can show with this reset mechanism is that that might not be true. That in fact, even just the act of, for a moment, stepping outside of your habits, if you go back to that topic, as a group, and just doing something completely arbitrary, right? Let's say dancing in a circle all night like the sun in South Africa. That actually has, on a system